Spectral decomposition is a technology that is now routinely used for seismic interpretation and characterization. Here's the train of thought that led to its development at Amoco Canada in the early 1990s. Most of the seismic data at that time was in the form of 2D grids. It was important to stabilize and balance the source wavelet across the available lines. This required analysis and corrections of amplitude and phase spectra at all line intersections and also at available well ties. Minimizing such wavelet variations is never an exact science. There are errors and uncertainties associated with both the seismic data and the well data. The goal was always to minimize wavelet mismatches within the grid and to end up with a wavelet that is approximately zero phase, so that for interpretation purposes, the seismic could be seen as a reasonable, albeit band-limited representation of reflective boundaries. For amplitude spectrum shaping, we would extract longer window-based spectra and use these as first-order estimates of the wavelet amplitude spectrum. When choosing an analysis window, we found that it was very important to steer clear of the highly reflective Cole zones. Whenever the Cole reflections were allowed to enter the analysis window, their high energy would swamp the content of the amplitude spectra. When we shortened the analysis window to cover just the Cole section, we discovered that the Cole-related spectral signatures would strengthen. These Cole-dominated spectral representations were showing us as much or more about the distribution of the Cole material as they were about the wavelet shape that we were really interested in. That was really the aha moment. The realization that if a short window around the Coles was telling us something about the distribution of the Coles, then why don't we see if a short window around a target zone could tell us something about the geological details of that target zone? This 2D line comes from an early 1992 attempt to use spectral decomposition to identify target zone geological details. Here are some of those highly reflective coals that we steered clear of when determining the operator for wavelet shaping. Down below is the zone of interest, a Devonian age reef buildup. This dip line spans from low reef to high reef through good porosity, fair porosity, and the tight reef. We shortened the analysis window to focus on the zone of interest, but kept it long enough to capture the tuning effects. We then proceeded to compute an amplitude spectrum for each target window input trace. The result was a tuning cube display as shown below the seismic. There are the same number of traces in the tuning cube as in the seismic data, but now the vertical axis is frequency. White and yellow are low amplitude, blue and red are high amplitude. And sure enough, we noticed that there was a nice correspondence between the spectral anomalies and the changes in the porosity. The tuning out that occurs at frequencies near 20 Hz corresponds with areas of higher porosity. For QC and calibration, we went back to the well log data that intersected this seismic line and created a 2D stratigraphic seismic model. Then we repeated the spectral decomposition steps on that model. It was reassuring to see that the modeled porous zone exhibited a similar tuning out at the expected frequencies. Early examples such as this gave us hope that this technique would prove useful.